Carl, don't forget to make me co-host.
Oh, I was just texting you that please log on so I can make you co-host. So.
I think I am there. I hope I'm in there.
Yep, if I can hear you, you're there. Co-host, you are now the co-host.
Thank you. So Carl, do you want to stop sharing so I can start sharing?
Yep. Okay, all yours.
Thank you. So we'll start at just a few seconds. I see people are testing out the chat. Excellent.
Somehow I cannot see the chat now, Dawn, because you're.
You should be able to see the chat.
I know, but I cannot see it now that I'm not sharing my desktop somehow. Sure.
Okay.
It's fine. I mean, once I share again, I'll see it. But if there's anything that I should know about, please let me know.
All right. All right, folks. So we'll start off with kind of some housekeeping because there's a lot of everything so new. So just an overview, we are going to provide live lectures and office hours and group work, but we will not require anything live because none of you signed up for doing things live. And we understand that, that it may not be easy for everyone. So we'll provide recorded lectures for this lecture that's going on right now. Will be recorded and uploaded later today. And you can get help via email or discussion boards, all these ways that the time of day doesn't matter. And we absolutely encourage you to work with other students. And there's so many ways to do it, you know, FaceTime or WhatsApp. You are all also can start your own Zoom meeting. So you can do that through Canvas, or you can make a free Zoom account at zoom.com. But also there's unh.zoom.com, I believe. I believe that's the place to go. So you can get it via your UNH username. And do let us know how we can support your learning. We understand that everybody's in a unique situation, in situations we can't even imagine. So use email, and we've also got this anonymous Google Doc that we listed on the March 17th announcements. Let me see if I can go there quickly. So if we go to announcements, yeah. So Hab 402 will go online after spring break. Way down at the bottom, here's the anonymous Google Doc. Okay, what else do I want to tell you? All right, just a few technical Zoom issues. We ask that you stay muted with your video off for the most part. But every once in a while at the 8 a.m., it was good to hear at least one or two people say, yes, I can see it, and so on and so forth. We will be using the chat today for questions. So while Carl is talking, I'll be monitoring the chat to see if there are questions, and I'll be answering the questions. And just a note that you can, if you look where your video is showing up, unfortunately I can't show you, but there are a couple of icons above the videos that let you toggle between who you see. So one of the options is just to show the video of the person who's talking, and that's probably what you want to do since there's so many of us. Carl, do you want to talk here? This is about the textbook.
Oh, yeah, sure. Am I, let's see, I lost my controls here, so I'm not muted, am I?
No, you're not muted.
Okay, so I just want to, first of all, thank you all for coming back. It is so good to see, quote unquote, see you all. I hope things are going well for most of you, for all of you. And what we're trying to do is maintain as close to normal as we can in this very abnormal time. There's a lot of new elements of the course. Dawn and I are doing our best to learn some new technology. Some of it is a lot of fun, and I hope that you guys enjoy it, and that maybe we can get something positive and productive and new out of it. But I also am very aware that this can be overwhelming, and we just want to mention that the backbone of the course is still the textbook. If you keep up with the suggested readings that we have on Canvas, and Dawn is taking you there right now. The lectures that I will be giving will be very close in content to what is covered in the textbook, the night versions and the OpenStacks, just as it was before we left on break. The videos will be posted in this particular place after the live recordings for people who have some difficulty in joining live. But if you still keep up with the textbook, and you still keep up with the material that's being covered there, you're going to be good. Okay, so everything else we're trying to build out from that, as we were building out before, as the lecture was a build out from the textbook before. We're trying to follow that model, and that's our goal. Dawn and I live on your feedback. If we miss the mark on this, we need to hear from you, like what parts are not working. So the other thing is, Dawn has this very nice Google Doc, and maybe she can show that where that is, or remind us where that is. That's, I think, the best place for you to tell us, hey, this is fine, or hey, I cannot see during the online lectures, your notes are illegible, or something like that. Or, hey, Zoom is a disaster, and I need some other solution. So please do give us, or otherwise, if it works good, please also, the positive feedback helps too. And we're starting to get some feedback on exams, which is great, right, Dawn? That's what you asked for in the 8 a.m. We're starting to get feedback. Thank you so much for that already. That's, so is that what you wanted me to say, Dawn? I don't.
Thanks.
Okay, yeah.
Yes. Just a couple other updates. Homework 5, which is on optics, things that we did before break. It's posted now on Mastering Physics and due next Sunday just before midnight. So hopefully that's the most familiar thing that doesn't need to change at all. There was one small problem, which was with diverging lenses. And because we never did an example in class, I made a short 5-minute video that's now available on Media Gallery, which you'll see in a minute, doing a lens example with a diverging lens. And the only difference is that there it is, that the focal length is negative instead of positive. So that just makes a small change in the mathematics, but the basic equations are still the same. And we also put up a discussion board for questions. So I expect to, here we go, put up a discussion board for every assignment. So one discussion board for each homework, one discussion board for each lab. So here's the discussion board on lenses. So you can post your own questions there, or maybe look there and see if somebody's already asked the question that you have. And indeed, there's one question already, which I can answer sometime today. So labs. The labs have to be very much put in quotes. It's going to be very different. So let me again go back to where online you can get these details. So I want to make sure that you can find these details later, anytime that you need them. So we're modules, course information, lab dates. So here are, we have the same lab schedule as we posted before. So we've only got 4 labs after spring break. And here's a couple of details. These are labs will now either be worksheets or will ask you to run an online simulation. You'll have a week from when we post the lab to when it's due. So I hope to post the lab sometime today, and it'll be due a week from today. And you'll upload it on Gradescope. So that will be that way. And then the lab TAs, so the new thing is the lab TAs will be available online, and it's kind of like a virtual office hours, a virtual lab. So what I've got down here in this table that's spread across 2 pages is the TA, the time that they're going to be there, and their Zoom link. So we've got 1 hour each day and different hours on each day. So hopefully those will work for folks. You don't have to show up. You can show up to anybody's lab. And if there's enough people to make a group, we can put you in a group in a breakout room and you can talk among yourselves. So we'll see how that goes. But you can also work in groups of your own making at your own times. And I think those are the main points on the lab. Oh, and lab this week is about the compound microscope with 2 lenses and 2 images. So it's using optics, going back to that. Exams is going to be more tough. I mean, we honestly don't know exactly how to do this yet. Oh, some people asked about exam 2. Yes, we know that exam 2 is in process of being graded and will be graded early this week. And I'll tell you right now, I'm so happy we did Gradescope this semester because we can get your exams back to you with the feedback in a straightforward way. So we're still working on how to give the remainder of the exams this semester. The 2 thoughts are to give it on Canvas, where you can do multiple choice or essay, where you can show your work, or paper, where you'd upload to Gradescope. And you would still have, still have a limited time, but a larger window. So we might say take 80 minutes sometime in this 24-hour window. And somebody pointed out at 8 a.m. that they're in a different country in a different time zone, so that's really important for them. So we have some ideas, but we certainly it's a work in progress about how this is going to go. And then finally, group work on Friday. One thing that Zoom does is breakout rooms. So we're hoping to use breakout rooms. So there'll be, we can do, people can work in smaller groups and you can chat with each other and you can virtually hold your hand up and have a facilitator come into your room. You can share your work by holding your paper to the camera or a Zoom whiteboard. So I may put up online a survey asking who you want to work with so that we can make some of those groups ahead of time. I think that's how it's going to go. All right. So if there are any questions, there is one question in the chat. So somebody's asking, can we set up a survey to see which options for tests are better? We can, although we're only going to be able to offer it one way. So one of the things that would be very helpful is to put in that anonymous Google Doc why one way or another is better for you. That would be very helpful. So we have a little bit of time to work this out. And we appreciate your patience and your feedback as we do that. Okay, Carl.
Okay, Dawn, was that a private chat or?
Oh yeah, it was a private chat, so that's
okay.
why.
So I'm just wondering if my chat had frozen or something.
No.
Okay. So what I'll try to do here is share my screen again. And is that?
I can see your screen.
Okay.
And oh, by the way, so people, Carl will be posting his PDFs as well as the video.
Yes, I will. Give me one moment just to try to manage my own desktop here. That's what I wanted. Okay. So welcome back, everybody. I am really happy to see we have something like, I saw 76 people on Zoom, and this seems to be working reasonably well. We'll see. As we said a couple times, we need your feedback, and we'll do our best to make this as productive and positive as we can. I have to apologize in the first part because I'm home in my studio, whatever you want to call this. I'm in my office. I have two daughters that may occasionally interrupt the lecture, and I hope you'll bear with that. Tomorrow we're going to have a rescue dog, which will certainly interrupt the lecture, and we'll see how this all works out. So, long story short, I'll try to keep this as professional as I can, but I'm not promising anything. Okay, so let's start with the lecture. The modern picture of the atom. What I'm trying to get to today, we have a modest goal. We just want to see Coulomb's law. So for reading along at home, what you want to work yourself up to is reading and understanding Coulomb's law. And I'm going to try to get you there together as a group today. So I need to start with a modern picture of the atom. What I'm talking about here is just any simple element like aluminum or iron or helium or silicon or something like that. If you dig down deep enough into this, what we're going to find is that this system consists of a diffuse electron cloud, which is of order 10 to the minus 10 meters. And there's a special unit for that. It's called an angstrom. 1 angstrom is 10 to the minus 10 meters. And that size is, I don't need you to memorize that. What I would like you to get away from this is that the entire size of the atom, which is defined by the size of this diffuse negatively charged electron cloud, is about 4 orders of magnitude bigger than the densely packed nucleus. And in the nucleus, we have 2 constituents, a positively charged proton and a neutral neutron. These are very similar objects to each other, except for the fact that the proton has a positive charge and the neutron is neutral. They're very similar to each other. They're both very much more massive than the very small electron. So they're about 2,000 times more massive. I don't need you to know the actual weights right now or the actual masses right now, other than to say that most of the mass, like the 99% level of the mass, is in the nucleus, and all the positive charges in the nucleus, the negative charge is in this diffuse, light, sparsely populated electron cloud that's very, very widely spread. The positive charge in our universe, for most part, is carried by the proton, and the negative charge is carried by the electron. One other thing that I'd like you to know is that if I come along and I try to pluck out an electron from this electron cloud, or if I try to pluck out a proton from this nucleus, these are two very, very, very different tasks. What we'll find is removing an electron is fairly easy by normal everyday standards. And you can prove this to yourself. It's a kind of a dry, wintry day. Put on a pair of fuzzy socks and walk across your shag rug, and then go up and shock your little sister on the ear. And in that process, you've liberated some electrons just by the friction of those two materials coming together. You've liberated some electrons and created a net positive charge in an atom by rubbing off some of those electrons. That is much more easier to do than the opposite, which another way we could make a net charged object is if we plucked out a proton from this nucleus. That is very difficult to do by everyday standards. It takes a tremendous amount of energy. It takes about 1,000,000 times more energy to remove a proton from a nucleus than it does to remove an electron from the electron cloud. The numbers don't matter for our purposes here, but the effort does. And all I want to say here is that it's much more easy to strip out an electron than it is to strip out a proton. So what's the net result here? If we start out with a net neutral object, like everything around us, like our desk, like your mouse, like yourself for the most part, if I want to make that a net charged object, the easiest way to do this is to strip off an electron. And what happens there is, in this picture at the bottom, I've knocked out one of those electrons, and I still have 3 positive protons in the nucleus. I have a net charge. I have an imbalance. And this is where we're going to get to Coulomb's law, is when we have this net charge, when we have a charge imbalance, is when we're going to experience electrostatic forces. The other way that we could do this is if we come in and we knock out that proton. I'm saying that is difficult in everyday practice, but for the purposes of this class, we could either have a positive or negative charge. This is the way that you would typically do that, is if you knocked out a positive proton, then I have an imbalance because I have more electrons than I have protons, and the balance is broken. You'd have a net negative charge. Okay, so an object, long story short, the easiest way for an object to become charged is if we gain or lose electrons. Now, let's get to the point where we actually have a charged object. And if I have 2 objects, let me scroll down so I'm not overwhelming you. I want to concentrate on this first part here. So if I have 2 objects, and by whatever means, by hook or by crook, I have created a net negative charge on these. And I hope you can see what I'm holding up here. So if I have 2 objects, and there we go, my camera kind of zooms in. I apologize for that, but it eventually focuses. So I have 2 objects that have a net negative charge on this guy, a net negative charge on this guy, and I hold them together. What I'm going to find is they don't want to come together. They have a repulsive force. They will tend to want to move apart from each other. By the same token, if I have 2 positive objects and I bring them close together, they're going to have a net positive charge, and they will tend to want to repulse from each other. They will tend to want to move apart from each other. And one second, okay. No, one second. Sorry. So, and then the final case here is if I have a positive and a negative charge. Where's my negative? What I'm going to find here experimentally, observationally, is that they tend to attract to each other. They will tend to move towards each other if they're allowed to. So we have a difference of result in electrostatic force depending on the positive or negative nature of the charge. I'm going to have to pause. I mentioned here earlier that I have to apologize for this kind of stuff. Girls, come in and say hi. Come in and say hi to everybody. Okay. My girls just want to say hi. Hello, everybody. All right. There we go. You guys doing okay?
Yeah.
All right. Say hello, and then let me get back to work.
Hi.
All right. Go ahead. Thanks a lot. All right. So that is our basic observation of charges, is that the direction of the force is going to depend on whether we have positive or negative charges. The other thing that we will find observationally, if we go into the lab and we put, two charged objects next to each other and measure the magnitude of force between them, say that I have these, say I have these two positively charged objects, and I measure the force between them. I know from my previous observation that they're pushing away from each other in this direction, but how much that they're pushing away, I can measure that force. And then if I move them a little bit closer, what I'll find is that magnitude of force becomes stronger, so that the force they're wanting to get apart from each other becomes stronger the closer that I get to each other. So what we find is there's a distance dependence on how far these objects are separated from each other. So that's our first observation. And okay, so thank you for the compliments on my daughters. And yes, I appreciate that. So the next thing I want to do is we get to SI units of charge, and this is just bookkeeping, but again, I think I've tried to hammer home as many times as I can that we can save ourselves a lot of trouble by using SI units of when we're doing our equations. What we're going to find in just a moment here, we'll see what's called Coulomb's law. It's a little bit uglier and a little bit more complicated than laws that we've seen before, but you can get yourself a little bit of a simpler challenge if before you ever start using this equation, you change things into SI. The SI unit of charge, and the reason for that is if I use the SI units when I go in, I know I'm going to get the SI units for the result, right? So the SI units for force are newtons. If I use the SI unit of charge for charge, then this will all make my life a little bit more simple later. So the unit of charge for SI is a Coulomb, and for our purposes, this is a huge amount of charge. It's named after a guy named Augustin de Coulomb. He was a French physicist from the late 1700s into the early 1800s, and he painstakingly measured the types of forces and the interaction between charged objects. This is named after him. It's a huge amount of charge. So the two objects that we've talked about so far, proton and electron that are charged, if we measure the charge on those objects in these units, the SI units, it turns out to be a very tiny number. So that means that this unit of Coulomb is a very large amount of charge. So one proton has 1.6 times 10 to the minus 19 coulombs. That's 1.6 with 19 zeros before it after the decimal point. So this is an incredibly small amount of charge. An electron, in order for that to balance the proton, is going to be equal and opposite in charge. It's the same number. If you look up this number on the web or in other textbooks, you'll see that there's a lot of digits of precision after the decimal point. I'm just rounding this off because we don't need that type of precision. We're not engineers here. We're not, making calculations that are life or death. But I also don't want you to get the false impression that this is some exact number, that it's 1.6 and there's nothing more after that. I've rounded it off just for simplicity. So that's the units of charge. If we if you have any questions, now is the time, please, to type them in. I'm going to move on now to actually showing Coulomb's law. I'll pause if we need to, otherwise I'm going to go ahead. But please do, if you have any concerns or if you have any questions, please do, and Dawn will monitor that. So moving on, we've made this experimental observation that, okay, these, there's either an attractive or a repulsive force. That's interesting because it's a new type of phenomenon in terms of if we deal with our most common force is the gravitational force. Gravitational force only attracts. When you have two objects, they always attract. We have a new flavor here in the sense that this electrostatic force can both attract and repulse. So we're going to try to figure out a formula for this. And what I'm going to do is I'm going to set up this problem just in terms of two objects. I have a charge 1 and a charge 2, and I hope that you can see my mouse here. So let me try to get something that I can draw with. Whoops. I can draw with. And so I have a charge 1, and I have a charge 2. And hopefully you can see that, and hopefully I can clear it.
Yellow's a bit hard to see. You might.
Yeah, I don't know why it went to yellow. Let's get, well, maybe red is the most visible, right? Okay, so drawing. Now what I have is I have two objects, so I have two forces that are possible. This guy can exert a force, Q1 can exert a force on Q2, or Q2 can exert a force on Q1, and I want to be able to discriminate between them. So what I've introduced, and it's hard, I'm sorry my handwriting, that's one constant of the course, no matter which high-tech formula or high-tech format that we deliver it in, is my handwriting is going to be terrible. This is supposed to say F2 on 1, and this is supposed to say F1 on 2. What I'm trying to do here is discriminate between these two forces because we have to maintain the ability to not only have two objects, but possibly 3 objects or 4 objects or 5 objects or thousands of objects that are exerting electrostatic forces on each other. So in order to discriminate between those two, I have to introduce this notation. Okay. So what I want to do is now take a look at this and pretend that I'm Augustin de Coulomb and measure this. And what he found is that we found that there's a distance dependence. We found that there's a directional dependence on whether this is same charges or opposite charges, positive, negative, or positive, positive, negative, negative. Those are my 3 options. And what he found is that when he measured this, that the force of 1 on 2, and what I'm showing here is this force here, so the force of Q1 acting on Q2 is going to be proportional to the charge of 1, proportional to the charge of 2, and inversely proportional to the distance squared between them. Okay? So this gets a little bit ugly because I put absolute value bars on this, like is done in your textbook. But this is all this is giving me is the magnitude of the force. We're not talking about the direction yet. It just gives me the magnitude. So if this is 1 Coulomb, this is 1 Coulomb, and this is 1 meter, then I would plug in 1 Coulomb here, 1 Coulomb here, and 1 meter squared here. And that's the physics of Coulomb's law. The bookkeeping notational part of it, the part that gives us the actual correct value, is we have to know the proportionality constant, and that comes from Coulomb's constant right here. And he measured this for us. It's 9 times 10 to the 9th Newton meter squared per Coulomb squared. Convince yourself, please, that these units, although they're ugly and intimidating, make sense, either by following along with me now or just with a pencil paper at home. We have coulombs here, we have coulombs here. So in the numerator, I have Coulomb squared. I get rid of it with this Coulomb squared in the denominator. In the denominator over here, I have meter squared. I get rid of that with this meter squared in the numerator of the constant. And then the only thing that's left is this newtons. So my force, the magnitude of it, comes out in newtons. So please do convince yourself that the units make sense. The last part of this is, which direction is this force going to point? Excuse me. And the last part of this is that to figure out which way it's pointing, towards the other object or away from the other object, is if they both have the same excuse me, if they both have the same sign, we're going to have a repulsive force. If they have an opposite sign, we're going to have an attractive force, just like what I talked about earlier. So positive, negative, these are going to be attractive. Positive, positive, they're going to want to push away from each other. And negative, negative, these are going to want to push away from each other as well. So that is our Coulomb's law. I'm going to pause here for a minute because I'm choking to death, and also to give you guys a moment to ask us some questions in the chat before we move on. So how is this being digested, guys? Is this okay? Do we have any questions from the audience?
I don't see any, but it may take people a while to think about them and type them.
Okay.
We got one. We got one.
All good so far from Sarah Blatchley. I am following along. Okay, great.
This is helpful, folks. It's so good to know you're out there.
Oh, and you learned this in general chemistry. This is interesting. Okay. I am surprised that they cover this in general chemistry, but I'm absolutely thrilled that they do. So far, it's good. A bit hard to read some of the text. Yeah, same as lecture, right? So I'm very sorry about that, Nathaniel, but I will try to do my better with.
Can you make it slightly larger? It looks like you have more room on your screen.
I could. That's a great idea. Let's try that. So how's that? Is that still visible?
Yeah.
Okay. So now that it's bigger, can Coulomb be negative? Yes, that's a great question. A Coulomb, the charge can be negative. What we're trying to do here is simplify your life so that you don't have to carry that positive or negative through. But yes, absolutely, the charge on an electron, for example, is negative 1.6 times 10 to the negative 19 coulombs. Absolutely, it can be negative. Okay. All right, that's better. Okay, so the only thing is, now that I'm using up most of my desktop with this, if I scroll past something too fast, please do in the chat, or by some means or other, let me know, hey, please go back, and I will absolutely do it. Okay, so we have another 16 minutes here. What I want to do is just finalize. I only have another 3-4 minutes of material here. I didn't want to overload you guys on our first lectures, but let's take a look at some numbers, right? Numbers always help. So what I want to do is take a look at the electrostatic force between an electron and a proton, and I'm separating them by 1/2 an angstrom. What's an angstrom? I go back up here. An angstrom is 10 to the minus 10 meters. It's a unit of length that's kind of useful when we're dealing with subatomic distances. So it's 10 to the minus 10 meters. I have 1/2 of an angstrom, so it's going to be 0.5 times 10 to the minus 10 meters. And all I'm trying to do here is put in some numbers and see what the order of magnitude of this force is. I know my Coulomb's constant. If you look this up on the web, you're going to find that this is also another big, ugly number that I've truncated down to a simple 9. It's 8.9, blah, 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 15 digits of precision, times 10 to the 9 Newton meters per meter squared per Coulomb squared. The charge of the electron and the charge of the proton is the same. It's that number I gave you earlier, 1.6 times 10 to the negative 19 coulombs. And the distance between them is 0.5 times 10 to the negative 10 meters. Can't forget that squared, okay? So And you notice that in order to get the magnitude of the force, so up here, I wrote this in this very complicated way, F with an arrow with an absolute value on it. Here, I'm looking at either the force of the electron on the proton or the force of the proton on the electron. So I've simplified this. The magnitude is going to be the same. I don't care about the direction, so I let off the arrow, and I just write an F for the magnitude. I put in that Coulomb's constant, 9 times 10 to the 9. I put in my charge 1, my charge 2 with no regard for whether it's positive or negative. And I put in the distance, I square it, pop this all into your calculator, and you'll get something that's about 9 times 10 to the negative 8 newtons. I've rounded this off again because we're not doing engineering. I just want you to see the order of magnitude of the size of the force, 9 times 10 to the negative 8 newtons. All right. I did it all in SI. I get it all in SI when I'm done. And because this is a negative charge and this is a positive charge, we have opposite charges. I know this is going to be attractive. These are going to want to move towards each other. Okay, sorry, my camera does weird things. They're going to want to move towards each other. It's not going to be repulsive. Now, this is in newtons. I'm absolutely sympathetic because I live in the United States. I don't think in newtons myself, even though I'm a physicist and I've been doing this for a long, long time. So what we want is to compare this to something that maybe makes a little bit more sense in the same units, or maybe is a little bit more familiar. So if we compare this to the gravitational force, if I have two objects, two apples, or a planet and the sun, or, you know, two ping pong balls or whatever, everything in our universe has a gravitational attractive force. We're attracted to the Earth. The moon is attracted to the Earth. We have this constant gravitational attraction. This force follows a similar 1 over r squared law, except that it's the mass 1, mass 2, and then the distance squared. And we have this gravitational constant, again, a big, ugly, scary number with terrible units to balance out all the units here and leave us with newtons. But if I put in the mass of an electron, which is incredibly small in kilograms, it's 9 times 10 to the negative 31 kilograms. The mass of the proton, which is 1.6 times 10 to the negative 27 kilograms, divided by this same distance. I'm saying that what I'm trying to do here is how much is the gravitational force between an electron and a proton compared to its electrostatic force at the same distance. So I put in the same distance separation, and what I'm going to get here is 4 times 10 to the minus 47 newtons. Notice my kilograms cancel out here, kilogram, kilogram, kilogram squared. My meter squared cancel out, so I get newtons, and I'm left with newtons. And this number is 10 to the 39 times smaller than that electrostatic force. So this gravitational force that we know and are very familiar with, and if you know well enough how strong it is, because if you walk out your window, you're going to crack your head if you fall down a flight, just one story of your building. That's how, everyday type of force. This electrostatic force is 10 to the 39 times stronger. It's tremendously stronger. This aspect of it is masked because for the most part in our everyday lives, there is not a net positive or net negative charge on most objects. Everything is to an amazingly balanced level canceled out, that the positive and negative charge in my shirt, in my head, in the desk in front of me are completely balanced to a very perfect level. But when we have this imbalance, these electrostatic forces can be quite tremendous compared to forces that we're familiar with. Okay, so that is the end of my lecture. Maybe again, we'll open this up to questions, or if anybody wants me to rewind the lecture notes back to some previous part here, I'm happy to do this. I open this up to you. One other thing that I wanted to try to get going, please do type in, if you have a question, please do type it in. Dawn, do you have the ability to start a poll?
No, I don't know why you don't have the ability to start a poll.
Every time that I tested this beforehand, I had the ability to start a poll. It's just not there on my menu anymore. It's very
You know what you can do, Carl? You can actually make me the host. I get to take over, and then I can just see if I can do it.
How can I, let's see, I'll try to do that. Make you, you are now the host.
All right.
Okay, you're now the host.
All
And
right.
yes, to answer your question, we are going to post the PDFs. Yes, absolutely.
That's so interesting. I don't see
I
that
think
we have
you know what, I must have done something weird when I set up the meeting. Like
Yeah, maybe you didn't allow.
I didn't allow polling. So we'll try that next. We'll try that next lecture. One other thing, you know, in lieu of, we used to have anecdote time, and you know, some people love this, some people didn't love this, but we can have, you know, we can have some fun with this. So what I'm going to invite you guys to do for our next lecture. Our next lecture is on Wednesday. It's going to be the exact same. It's going to be the exact same link. We'll send it out again. But if you were able to log on with the hyperlink that you used to log on today, it will be the same link. It will be the same exact Zoom meeting. And when I finally post, I'm going to post some office hours, virtual office hours. It'll be the same Zoom meeting for that. So you can kind of bookmark that or save that, and hopefully that is going to be trivial. Question from Owen Hamill. You are not going to need to know the gravitational force equation. It's just to compare to the other equation. To me, as a physicist, whenever we start seeing similarities in things that are dissimilar, it's interesting to me. I just find it very fascinating that both the electrostatic force and the gravitational force has this almost identical structure. You have the distance squared in the denominator, and then you have some characteristic, some intrinsic property of the object in the numerator, the mass for the gravitational force, or the charge for the electrostatic force. And then you have some bookkeeping nonsense, some horrible number just to get the numbers right. But the physics here is really there. But no, I don't need you to memorize that at all. I was hoping just to give you some sense of, you know, electrostatic forces are tremendously powerful compared to gravitational forces. That's all I wanted you to get from that. This may sound stupid, but did you say that the 10 to the 39 number means there's a strong force? I mean that that the electrostatic force is way stronger than the gravitational force. Peyton L. So that is, I'm just saying that the electrostatic force is way stronger than the gravitational force. You're jumping ahead of us into nuclear physics, and I love where you're going with this. There is a strong force. It's even stronger than the electrostatic force, about 10 orders of magnitude more. You don't need to know it. I'm not trying to make you guys nuclear physicists, but excellent question, and thank you for asking it. So the last thing I wanted to mention is, maybe for Wednesday when we have the next one, I can do all kinds of weird things here. We're learning the technology of how to do Zoom. So I can put myself in space. I can put myself in the forest. Can you guys see this, hopefully?
Yes.
I can put myself in danger. So if you guys have interesting backdrops that you'd like me to broadcast the lecture from, please go ahead and send them. And I'm happy to, maybe at the beginning of next class, we will have a vote on whether I should just have, you know, the sheet hanging behind me, or if we should have something more interesting like dinosaurs or things like that. Stephen Lambert, thank you for the efforts. You're very welcome. And I really am so happy to see all of you in some sense or not. I hope that, you know, we can continue, and we're you know, Dawn and I really have, you know, a lot of ambition that this can be a positive thing in a very weird situation. So thank you for your feedback. We'll do our best. Thank you very much.
So we can stay online a little bit longer if people want to ask questions, and otherwise we'll see you Wednesday. Oh, it looks like the dinosaurs are winning. So
Dinosaurs.
there you go.
Okay.
Yes, thanks for everyone. Thanks for your comments in the chat. It really does feel like we're still connected and still in the same place, which is lovely.
Did we miss anything from the earlier lecture, Dawn? Did we talk about anything that we didn't talk about here?
No, I think we're good.
Yeah.
Good.
I guess we got maybe a little bit. Okay. Let's see what the comments are. Thank you. Also, yes to dinosaurs. This is a
Velociraptors.
fun, nutty new system. Yes, it is a fun, nutty new system. Would like to see some velociraptors. Okay. So, please inbox me with where you want me to be during the next lecture, and I'll you know, if we can, we'll put it up there. Thanks so much, everybody.
Thanks. So we'll stay on for just a little bit and see if people have questions, but otherwise I'm gonna.
Do you want to reiterate what's going on with labs, Dawn? Just, I guess, maybe what's happening this week?
Oh, we have a serious question here. Why did you disregard the charges in your first example?
Okay, let me get back to my first example. Is this the example? This is Sierra?
Yeah, he says yes.
Sierra, hopefully I'm saying your name right. I apologize if I'm not. So I did not disregard the charge. I disregarded the sign. And because this is a serious question, let me turn off my dinosaur. So I disregarded this. This is an electron. If we go back up here to the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. The charge of the proton is the same number, but positive. What I'm going to do in this Coulomb's law is disregard the sign, not exactly the charge, not the magnitude, but the sign. So I threw away that negative, and I just put in the absolute value here. And then once I'm done, so this is how, I'm following the pedagogy of your book, which is just disregard the signs when you first start this up. It tells you the magnitude. And then I go to this little box here, and I figure out whether they're going to be, if they are the same sign, they're going to be repulsive and pushing each other away, and that's for minus, minus, or for plus, plus. And if I have an opposite sign, they're going to be moving towards each other. It's going to be an attractive force. So back to your question, we have an electron and a proton, positive, negative. They are going to be attracted towards each other. They're going to be pulling towards each other. First, I get the magnitude of it, and then I get the direction. I hope that that helps answer Sierra's question.
Yep.
Okay, good. Thank you, Sierra.
Cool.
Can you just remind me of the A with a circle above it? Oh, okay. Peyton L is asking us A with a circle above it. That is an angstrom. That is the unit of distance. 1 angstrom, if I can try to draw this. 1 angstrom equals, I have to get an iPad so I can draw things a little bit better. But 1 angstrom, Peyton, is equal to 10 to the minus 10 meters. Is that your question? Okay. That's an angstrom.
There's a question, is that always true? So I'm not sure what that's in reference to, Hunter. So the business about the signs just telling us about attraction and repulsion? Yes, angstrom is a constant.
Oh, yes. Yes, it is, Hunter. That's always true. 1 angstrom is always 10 to the minus 10 meters. It's a definition, like 1 centimeter is 10 to the minus 2 meters.
All right.
And we have one last comment from Peyton. I think to everybody, good luck everyone with your classes. And I echo that. Good luck everybody. It's really good to see you all. Thank you for joining and bearing with us as we test out this new technology. Thank you so much.
All right.
Shall we stop, Dawn?
I think so. So if you have any follow-up questions, email is a good place. So take care, everybody. Have a good day. So Carl, we can talk in a minute about getting the video up, right?
Yep.
All right. See you in a bit.